Morning, one and all. Today we are going to discuss the topic is general properties of D block elements. Those are physical properties, atomic and ionic sizes, and ionization enthalpies, oxidation state of D block elements, and colored ions, and catalytic properties, magnetic properties, and formation of complex compounds, and formation of interstitial compounds. These are properties of D block elements. Now we will discuss the physical properties. Physical properties of transition elements. The transition metals are known as typical metals because of their physical properties. They are lustrous, that means bright and shiny. And D block elements are hard and strong, and they have high densities, and they are malleable. That means can be bent and pressed into different shapes, and ductile. That means can be drawn into wires. And they are act as good conductors of heat and electricity. And they have high melting and boiling points, except mercury, because of which is liquid at room temperature. D block elements are very hot, very much hard, except zinc, cadmium, and mercury. Because of these d orbitals are fulfilled with the electrons. That means zinc, cadmium, mercury do not have any unpaired electrons, so that these are very soft. But remaining elements are very hard because of they have unpaired electrons, and they have highest boiling and melting points. Because of the boiling and melting points are directly proportional to the number of unpaired electrons. So participation of more number of unpaired electrons from the d subshell and outermost shell of ns orbitals in intermetallic bond formation, so that they have highest melting and boiling points. Because of these are involved in strong interatomic bonding. Example, fifth group elements. Fifth group elements are chromium, molybdenum, and tungsten. These are having high melting and boiling points because of they have 6 unpaired of electrons. These are from the d subshell and outermost shell of ns orbital. D subshell have 5 unpaired of electrons, and ns subshell has 1 unpaired electrons. So total 6 unpaired of electrons. These 6 unpaired of electrons are participating in intermetallic bond formation, so that they have highest melting and boiling points. So in moving along the period from the left to right, the melting point of these metals first increases to maximum and decreases regularly towards the end of the period. The melting point of these metals rise to maximum at D5. The melting point of these metals rises to maximum at D5. D5 configuration elements are chromium, molybdenum, tungsten. So after these group, the melting points are decreases regularly as the atomic number increases end of the period, except manganese and technetium. These are have anomalous values. Then trends of melting point of 3D, 4D, and 5D transition metals. The strength of interatomic bonds in transition elements is roughly related to number of half-filled d orbitals. Number of half-filled d orbitals are nothing but number of unpaired electrons. Then which elements has the number of unpaired electrons? So then those are participating in intermetallic bond formation. So then they have highest melting and boiling points. Then in the beginning, the number of half-filled d orbitals increases. Yes, up to here, chromium, manganese, and tungsten, chromium, molybdenum, and tungsten. From starting to this group, from chromium, molybdenum, and tungsten, in the beginning the number of half-filled d orbitals increases till the middle of the period. Middle of the period is nothing but up to this group. Okay, and causing increase in the strength of interparticle bonds. But thereafter, the pairing of electrons in d orbitals occurs. After this group, the electrons takes place pairing. So whenever the electrons takes place pairing, the unpaired electrons are decreases. Whenever the unpaired electrons are decreases, then melting points also decreases. So that the initially the melting points of each group of the elements increases till middle. After that, the pairing of electrons takes place. Then the melting points of these elements also decreases up to end of the each period. Next goes to enthalpies of atomization. This is also depends upon the number of unpaired electrons. D orbitals of the elements has high enthalpies of atomization. The maximum is at about the middle of the each series. Okay, where middle of the each series is nothing but same as usual. Now I told you just now, these are the chromium, molybdenum and tungsten groups up to here. So up to here, the maximum, the atomization of enthalpy is a maximum of each series. The large number of unpaired electrons take part in bonding. Because of the large number of unpaired electrons take part in bonding. So they have very strong metallic bonds and hence high enthalpy of atomization in group. Then what about in periods? Sorry, it is in period. Then what about in groups? The order of enthalpy of atomization in 5D series is greater than the 4D series of elements and next greater than the 3D series. Because of higher elements exhibit the metal bonding. That means here the 5D series of elements, exhibit the metal bonding, so that they have high enthalpies of atomization. Next goes to atomic and ionic sizes. What is the atomic size or atomic radius? The distance between the center of the nucleus and outermost shell of an atom. The distance between the center of the nucleus to outermost shell of an atom is called atomic radius. Then how it vary in a group and period of the d block elements? In a period, if you observe in a period from left to right, initially in a period of the d block elements from left to right, initially an increases atomic number, the atomic radius is decreases. From scandium to chromium in 3D series, from yttrium to molybdenum in 4D series, and from lanthanum to tungsten in 5D series. On increasing atomic number, the atomic radius is decreases. If you observe here, these are the atomic sizes in picometers. Here the scandium atomic radius is 162 and titanium 147 and vanadium 134 and chromium is 127. Here, but atomic number scandium is 21, titanium 22, vanadium 23 and chromium 24. What happened in a period from the left to right? The atomic number is increasing. Here it is 21, next 22 and 23 and chromium is 24. Okay. Initially, the atomic number is increasing from scandium to chromium in 3D series, but the atomic radius is decreasing. So these are atomic radius values. Here the atomic radius is decreasing from scandium to chromium in 3D series and yttrium to molybdenum in 4D series and lanthanum to tungsten in 5D series. What is the reason? Because of the inter-electronic repulsions. Because of the inter-electronic repulsions are very less than the nuclear charge. That means here the nuclear charge is dominating the inter-electronic repulsions due to poor shielding effect. Due to poor shielding effect. Because of here, the small number of electrons are present. Up to here, from initial scandium to chromium, the number of electrons are very less. And I mean, these are unpaired electrons. That is the reason the inter-electronic repulsions is not greater. But the nuclear charge is more due to the poor shielding effect. That is the reason, and initially an increasing atomic number, the atomic radius are decreases. Then in middle, an increasing atomic number, the atomic radius remains almost same. Some from where to where, from which element to which element, from in 3D series from manganese to nickel. 3D series from manganese to nickel. If you observe here, the atomic radius is, its manganese atomic radius is 126 picometers, iron 126, and cobalt 125, and nickel 125. Almost the atomic radius are similar, even though increasing the atomic numbers. Okay, manganese 25, iron 26, cobalt 27, and nickel 28. These are atomic numbers. But here, even though the increasing on atomic numbers, the atomic radius remains constant. From in 3D series from manganese to nickel, in 4D series from technetium to palladium, and in 5D series from rhenium to platinum. What is the reason? Because of inter-electronic repulsions is equal to nuclear charge. In this middle of the every period, the inter-electronic repulsions are equal to the nuclear charges. Because of this inter-electronic nuclear charge balanced by the repulsions between the shared d electrons. If you observe here graph, in this here, the manganese, iron, cobalt, and nickel, they have almost, in 3D series, they have almost similar atomic radius values. In 4D series, technetium and ruthenium and rhodium, these are also having the, up to palladium, they are also having the similar atomic radius values. Next goes to in 5D series, rhenium, osmium, iridium, and platinum. They are also having the similar atomic radiuses. This is in middle of the every period of the d block elements. Then what happened in this last? Okay, in last, an increasing atomic number, an increasing atomic number, the atomic radius is increases from here copper to, from here copper to zinc, in 3D series. In 4D series, silver to cadmium, and in 5D series, gold to mercury. If you observed here atomic radius values, then it is easily understood. Okay, in last, an increasing atomic number, the atomic radius increases. What is the reason? Because of in this the number of electrons pairing takes place, so number of electrons are increasing. So inter electronic repulsions are increases than the nuclear charge. That means here the inter electronic repulsions are dominate the nuclear charge. Whenever the inter electron repulsions takes place, then it leads to the electron cloud expansion. Whenever the electron cloud is expansion, so size is increases. Because of here, d orbital is fulfilled with the 10 electrons and shields the electrons present higher orbitals. So in these first B group series of the elements, in this first B group series of the elements has bigger size than its earlier elements in this block. That is the reason the atomic radius initially decreases, then in middle constant almost same, and in last the atomic radius increases even though atomic numbers are increasing. What about in group? In group, from top to bottom, the sizes are increases. We know that from top to bottom, the sizes are increases because the number of shells are increases. Because the number of shells are increases, so that the atomic sizes are increasing. Then what about the period? In period, the atomic number increasing, but the atom generally the atomic number increasing, but atomic radius is decreases because of the electrons, the outermost electron, that is the last electron, is entering into the same shell. That is the reason generally in a period the atomic radius is decreases even though increasing the atomic number. But in a group, generally the atomic radius is also increases with the increasing atomic number because of the lost electron is enters into new shells. That means the number of shells is increases. So in this one also, from scandium to yttrium and yttrium to lanthanum, the atomic radius are increases, increasing number of shells dominating over the nuclear charge from 3D to 4D series. Then what about from the 4D series to 5D series? The 4D series to 5D series elements have almost similar sizes due to lanthanide contraction because of poor shielding effect of 4s orbital electrons. Here, if you observed here, from 3D series to 5D series, from 3D series to 5D series, the atomic sizes are increasing. Okay, from 3D series to 4D series, the atomic sizes are, or atomic radius are increasing. But from the 4D series to 5D series of elements, from the, this is the 4D series, from 4D series to 5D series of elements, the atomic sizes are almost similar because of lanthanide contraction. What is the lanthanide contraction? What is the lanthanide contraction? The sizes are, the sizes are decreasing even though increasing atomic numbers. Okay, the sizes are decreasing even though increasing atomic numbers because of poor shielding effect of orbitals of the electrons, because of poor shielding effect. Okay, then now we will observe here 4D series to 5D series. For example, zirconium to hafnium. Zirconium atomic radius is 160 picometers and hafnium is 159, and niobium to tantalum, here niobium 146 and it is also 146, and molybdenum and tungsten 139 and 139. Almost the 4D series of elements having similar to the 5D series of elements in their atomic sizes because of lanthanide contraction due to the poor shielding effect. Okay, the lanthanide contraction is not observed in the yttrium and lanthanum. This is the lanthanide contraction is not observed in the yttrium and lanthanum because of here the yttrium atomic radius is 180, here the lanthanum is 187. The difference is very large, so that it is not observed. The lanthanide contraction is not observed in yttrium and lanthanum because of they have no 4f orbital electrons, because of they have no 4f orbital electrons. That is the reason the lanthanide contraction is not observed in yttrium and lanthanum. Then density. What about the density? Then here it is increases from the third B group to first B group elements. Density is increases from the third B group to first B group element. Then it is decreases to second B group. Here third B group to and first B group elements increases density, and then next from first B group to second B group elements decreases. First third B group is nothing but scandium, and first B group is nothing but copper. That means the scandium to copper elements. From the scandium to copper, in a period, the density is increases, and from copper to zinc, and from copper to zinc. Here the copper is belongs to first B group element and zinc is belongs to second B group element. From copper to zinc, the density is decreases because of the density is inversely proportional to the atomic sizes. Because of the density is inversely proportional to atomic sizes. Inversely proportionality is nothing but if the atomic sizes increases, then what happened? The density is decreases. If the density is increases, the atomic sizes are decreases. That is the relation between the density and atomic sizes. Ionization enthalpies. What is the ionization enthalpy? The amount of energy is required to remove an electron from the neutral gaseous atom to form the ion is called ionization enthalpy. What is the ionization enthalpy? The amount of energy. The amount of energy is required to remove an electron from the neutral gaseous atom to form ion. That is called ionization enthalpy. Already we studied in first year what is the ionization enthalpy, what is the first ionization and the second ionization. Okay, I hope you know about the ionization enthalpies. Then due to increase in nuclear charge, due to an increase in nuclear charge, there is an increase in ionization enthalpies. That means the ionization enthalpy is directly proportional to the nuclear charge. If the nuclear charge increases, then what happens? The ionization enthalpy is increases. If the nuclear charge is increases, the ionization enthalpy is also increases, because of these two are directly proportional to each other. So due to an increase in nuclear charge, there is an increase in ionization enthalpy along each series of the transition elements from the left to right. The ionization enthalpies give some guidelines concerning the relative stabilities of oxidation states. Although the first ionization enthalpy in general increases, the magnitude of these increase in the second and third ionization enthalpies for the successive elements in general is much higher. Mostly, we know that the IE3, third ionization enthalpy is greater than the second ionization enthalpy, and the second ionization enthalpy is greater than the first ionization enthalpy in each group. Next goes to one of the properties, oxidation states. Okay, oxidation states. Generally, the D block elements they exhibit the more than one oxidation states. Okay, the D block elements exhibit the more than one oxidation states. That means they are exhibit the variable oxidation state. Okay, that means they can form two or more different types of cations. For example, iron can form both Fe plus 2 and Fe plus 3 ions. And one more example, manganese, it can also forms the Mn plus 2, Mn plus 3, Mn plus 4, Mn plus 6 and Mn plus 7. Like this, all the transition elements exhibit the variable oxidation states and forms the different ions. Because of why these exhibit the variable oxidation states? Because of involvement of D subshell of the electrons and outermost shell of Ns electrons in bond formation. Because of involvement of D subshell of electrons and outermost shell of Ns electrons in bond formation, there is a reason all the transition, most of the transition elements exhibit the different more than one oxidation states. These are the oxidation states. These are the oxidation states of the first row of the D block ions. Okay. In this, the red marks, that means the red colors are most stable oxidation states of the corresponding metals, and this pale blue, these pale blues are rare oxidation states of the corresponding metals. Here, the scandium exhibit the plus 3 oxidation states. Here, titanium plus 2, plus 3 and 4. And vanadium from 1 to 5. They exhibit the 1 to 5 oxidation state. And chromium also, they exhibit from the 1 to 6 oxidation states. And manganese exhibit the from 1 to 7 oxidation states. Iron exhibit the 1 to 6 oxidation states. And cobalt exhibit the from 1 to 4 oxidation states. And nickel exhibit the plus 1 and plus 2 plus 3 and plus 4 oxidation states. And copper exhibit the from 1 to 4 oxidation state. And zinc exhibit the only plus 2 oxidation state. Here, scandium exhibit the only 3 oxidation state, and zinc exhibit the only plus 2 oxidation state. Here, maximum oxidation state. Maximum oxidation state 3D is exhibited the manganese, that is the plus 7 oxidation state. What is the lowest oxidation state? 1. It is exhibited the copper mostly because of it is a stable oxidation state of the copper. Here scandium is only one possible ion because of it exhibit the only +3 oxidation state, and zinc is also possible only one ion because of it is also exhibit the only +2 oxidation state. If you observe these oxidation state, scandium and zinc, this is the scandium and zinc do not exhibit the variable oxidation states because of the scandium its 3 electrons and zinc its 2 electrons. Okay, scandium plus has electronic configuration of argon. After it lost its 3 electrons, then it gets the only argon electronic configuration. After it get the argon electronic configuration, it is stable, so that it is impossible to remove the electrons from this scandium, so that it is exhibit the only +3 oxidation state. Same as well zinc exhibit the only +2 oxidation state. Whenever it lost the 2 electrons, it gets the +2 oxidation state and it gets the argon 3d10. This is also not possible. From this one also impossible to remove the electron. So these are not exhibit the other oxidation states. Then except scandium, all the elements are +2 oxidation state. Here, except scandium. If you observe here, except scandium, all the elements exhibit the +2 oxidation state. And except zinc, all the elements have +3 oxidation states. Okay, here except scandium, all the elements exhibit the +2 oxidation state, and except zinc, all the elements exhibit the +3 oxidation states. Okay, the highest oxidation state is +7, exhibited the manganese. Okay, in this 3D series, the manganese exhibit the highest oxidation state, that is +7, because of this is corresponds to the removal of all d and 4s electrons. These 7 corresponds to the all removal of 3 and 4s electrons. This is the maximum oxidation state. The maximum oxidation state is never greater than the total number of 3d electron and 4s electrons. Okay, you remember this? Maximum oxidation state is the maximum oxidation state is never greater than the total number of 3d and 4s electrons. Okay, then lowest oxidation state is exhibit the copper, that is +1. It is stable oxidation state. Okay, then common oxidation state is +2. Okay, it is exhibit the zinc. It's a stable oxidation state. It is exhibit the zinc in Gen SO4. In highest oxidation state in 3D series. Highest oxidation state in 3D series +7. That is exhibit the manganese in KMnO4. And highest oxidation state in D block. Total highest oxidation state in D block is +8. It is only in 3D series. Okay, highest oxidation state in 3D series +7, that is exhibit manganese, that is observed in KMnO4. Okay, if you calculate the oxidation number of manganese KMnO4, they will get +7. Next goes to highest oxidation rate in total D block is +8. Okay, this +8 is exhibited ruthenium and osmium. These are belongs to 8th B group elements. Okay, these are belongs to 8th B group. Here, the ruthenium is exhibited the +8 oxidation state in RuO4, and osmium exhibit +8 oxidation state in SO4. If you calculate the oxidation numbers of oxygen in these, then you automatically get the +8 oxidation states. These are most important for competitive purpose. Then you will remember these points. Next is the one of the property of transition elements, magnetic properties. Okay, they exhibit the paramagnetic and diamagnetic and ferromagnetic properties. We know that these are already we studied in solid state lesson. What are the magnetic properties? Okay, then when a magnetic field is applied to substance, when a magnetic field is applied to substance, mainly two types of magnetic behaviors are observed. Mainly, whenever the magnetic field is applied to substances, mainly we two types of magnetic behaviors are observed. Those are diamagnetism and paramagnetism. What are the diamagnetic substances? What are the diamagnetic substances? That means how can we identify the given compounds are diamagnetic substances? Okay, the diamagnetic substances are whenever we applied the magnetic field to the diamagnetic substances, those are repelled by the applied field. Those are repelled by the applied this external magnetic field. Then those are the diamagnetic substances. If we applied the magnetic field to the paramagnetic substances, then those are paramagnetic substances are attracted by the external magnetic field. Okay, whenever the magnetic field is applied to the diamagnetic substances, if the substance whenever the magnetic field is applied to the substances, thus if the substances are repelled by the external magnetic field, then those substances are belongs to the diamagnetic substances. Okay, if whenever the magnetic field is applied to the substances, if those substances are attracted by the external magnetic field, then those are belongs to the paramagnetic substances. Okay, the substances which are attracted very strongly, substances which are attracted very strongly by the external magnetic field are said to be ferromagnetic substances. In fact, the ferromagnetism is an extreme form of paramagnetism. Okay, the most of the transition elements and their compounds show the paramagnetism because of they have almost most of the elements have the unpaired electrons in their d orbitals, so that shows the most of the element shows the paramagnetism. Paramagnetism arises from the presence of unpaired electrons. The paramagnetism arises from the presence of unpaired electrons. The diamagnetism is arises from the absence of unpaired electrons. Okay, paramagnetism arises from presence of unpaired electrons, whereas diamagnetism is arises from the absence of unpaired electrons. Here, each such electron have the magnetic moment. In this d block elements, each unpaired electron have a magnetic moment. Transition metals usually contains unpaired electrons, we know that. So these are exhibit the paramagnetism. Paramagnetic behavior increases with the increase in unpaired electrons. Paramagnetism is expressed in terms of magnetic moment. Here the paramagnetism is expressed in terms of magnetic moment. So it is related to number of unpaired electrons. Here the magnetic moment is related to number of unpaired electrons. The magnetic moment calculated from the spin only formula. The magnetic moment of every atom or ions of the d block elements calculated from the spin only formula, and those derived experimentally from this formula. Magnetic moment mu is equal to under root of n into n plus 2 bm. Here mu is nothing but a magnetic moment, whereas mu is a magnetic moment. Here n is the number of unpaired electrons. Here n is the number of unpaired electrons. And what is the bm? These are units. These are units of the magnetic moment. bm is nothing but Bohr magneton. bm is nothing but a Bohr magneton. It is the units of magnetic moment. Then this is the formula is used to calculate the magnetic moments of the transition elements. You remember this formula. Okay, these are magnetic moments of each ion. The magnetic moment of the each ion. Scandium plus 3. Scandium plus 3, whenever it lost the total electrons, then it has, that's whenever it lost the total 3 electrons from the 3D and 4s, then it has now 0 electrons 3D orbital. So unpaired of electrons is nothing but 0 here. So here the magnetic moment value is also 0. Here whenever the n is equal to 0, then value is also automatically we get the 0. Okay. Then titanium and next goes to vanadium and chromium, manganese, iron, cobalt, nickel. These are ions of the magnetic moments. How to calculate the magnetic moment given ion? Now we will calculate after this point. Then generally the D0 and D10. D0 and D10. This point D0 and D10. D0 is nothing but D orbital do not have any electrons. D10 is fulfilled with the electrons. Okay, D0 and D10. D0 and D10 elements exhibit the diamagnetic nature. Okay, D0 and D10 ions are elements mostly D block elements exhibit the diamagnetic nature. For example, zinc. Actually, zinc atomic number is 30. Okay, so its outermost electronic configuration is 4s3d10. Zn plus 2 is taken. Zn plus is nothing but it lost its 2 electron. Okay, whenever it lost its 2 electron from the 4s orbital, then now it has only 3 electrons. So 310 means completely filled. Here the d orbital is completely filled. So it has no unpaired electrons in its d orbitals. So that it's with the diamagnetism, because of whenever it is external magnetic field is applied to the Zn plus 2 ion, whenever the external magnetic field is applied the Zn plus 2 substance, then it does not have any unpaired electrons, so that it is repelled by the external magnetic field. So the repelled external magnetic field of the substances are diamagnetic substances, because of it has no unpaired electrons in its d orbital. So Zn plus 2 is exhibit diamagnetic nature. Next goes to Mn plus 2. Mn plus 2. Actually, the manganese atomic number is 25. Its outermost electronic configuration is 4s2 3d5. Okay, it has Mn plus 2. That means it lost its 2 electrons. Whenever it lost its 2 electrons from the outermost shell of 4s electron, now it has 3. Now it get the 3d5. Now it has 5 unpaired electrons in its d orbitals. Now it has 5 unpaired electrons in its d orbitals. Then now whenever the external magnetic field is applied to the this Mn plus 2 substance, then it is attracted by the external magnetic field. Whenever the substance is attracted by the external magnetic field, then the substance is paramagnetic substances. Yes, so it is attracted by the external magnetic field because of it has unpaired electrons. It has unpaired electrons, so that whenever the external magnetic field is applied to the substance is attracted by the external magnetic field because of it has unpaired electrons, so that it exhibits the paramagnetism. I hope you understood what about the diamagnetic and paramagnetic substances. Then how to calculate the magnetic moment of transition metal ions. How to calculate the magnetic moment of transition metal ions. For example, Fe plus 2 ion. For example, Fe plus 2 ion. How to calculate the magnetic moment? The magnetic moment the transition metal ion is calculated from the this formula. Okay. Now you will write formula magnetic moment mu is equal to under root of n to L s to Bm. Bm is nothing but a Bohr magneton. The N is nothing but number of unpaired electrons and mu is nothing but magnetic moment. Okay. Then we will calculate now magnetic moment of Fe plus ion. Generally, the iron atomic number is 26. Okay. Then its outermost electron configuration is argon 36 2. Okay. But here in the question, what is given? F plus 2 is given. Okay. Then Fe plus 2. Fe plus 2 is nothing but it lost its 2 electron from its outermost shell. What from where it lost electron? From its outermost shell of the force orbital. Okay. Whenever lost its 2 electrons from the force orbital, now it has only 6 electrons in its 3D orbit. So now you fill up these electrons, these d orbitals. And here, if you observed here, after filling up these electrons, now here 4 unpaired electrons present. Okay, 4 unpaired electrons are present. So here the n is equal to what? Here 4. N is equal to is what, Nana? Number of unpaired electrons. Number of unpaired electrons. Here the n is equal to 4. Then now you substitute this n is equal to 4 value in the above formula. So here 4 into 4 plus 2. 4 into 4 plus 2 Bohr magnetron. Okay. 4 into 4 plus 2 is nothing but 4 plus 2 is 6. 6 into 4 is 24. Under root of 24 Bohr magnetron. That is equal to under root of 24 is equal to 4.9 Bohr magnetron. It is the magnetic moment of the Fe plus 2 ion. Fe plus 2 ion mu value is 4.9 Bohr magnetrons. Then I will give one more example. This is a different type of questions possible to ask in any competitive purpose. Calculate the magnetic moment of divalent ion in aqueous solution if its atomic number is 25. Okay, here the atomic number is given. What is the atomic number in this question? 25. 25 is Z is equal to 25. So Z is equal to 25. Element is manganese. We knew that. Okay, Z is equal to, that means atomic number 25, element is manganese. Okay, then manganese is given, but here it is a divalent ion. Divalent is nothing but it lost its 2 electron. Okay, divalent is nothing but it's lost its 2 electrons. So it is the Mn plus 2 ion. So from this question, it is the Mn plus 2 ion. Then how to calculate now magnetic moment of this Mn plus 2 ion? Same as usual, you will write first of all formula, that is magnetic moment mu is equal to n into n plus 2 under root of n into n plus 2 Bohr magnetrons. First of all, you will write the manganese atom. Its atomic number is 25. Its general electronic configuration, outermost electronic configuration is argon 3d5 4s2. Then here, what is given in this question? Mn plus 2 ion. Calculate the divalent ion of the Z is equal to 25 magnetic moment. Yes, is this Mn plus 2. Mn plus 2 is nothing but it lost its electron from its outermost orbital. So it lost its electron from the 4s orbital. Then now it has 3d5. Here the d orbital has 5 electrons. These 5 electrons are unpaired electrons. So what is the n value? N is equal to 5. So this 5 is substituted in this above formula. So mu is equal to 5 under root of 5 into 5 plus 2 Bohr magnetron. Here mu is equal to, then what we get? 5 plus 2 7. 7 in 5 is equal to 35. So mu is equal to under root of 35 Bohr magnetrons. Then under root of 35 is equal to 5.92 Bohr magnetrons. That is the mu value of this divalent ion. That is the magnetic moment value ion in our solution. Its atomic number is equal to 25. Now ask yourself question. Calculate the spin only magnetic moment of M plus 2 ion in aqueous solution. Its atomic number is 27. Okay, Nana? Calculate the spin only magnetic moment of M plus 2 ion in aqueous solution. Its Z is equal to 27. So you calculate magnetic moment of this Mn plus 2 ion and send your answers. Then how to remember easily mu values? How to remember easily mu values? If number of n is equal to here, number of unpaired electrons. If n is equal to 1, then easily you remembered if the n is equal to 1, automatically you will get the mu value is 1 point something. So you remembered just 1. Okay.
Swapna madam.
If the n is equal to the
Conclude madam.
okay, sir. Thank you. Okay. Next we will discuss on tomorrow.